Greetings, Panthers. It is Dr. Augustine. I hope you all are doing well. I'm going to actually make a bonus video on how to use the Henderson Hasselbalch equation and why it's such an effective tool. Remember, Henderson Hasselbalch equation can be used anytime you have a buffer system. Okay, so if you have a buffer system, my advice is to use the Henderson Hasselbalch equation. It's derived from the Ka expression, so it comes from the fact that you have a weak acid of some sort. In this table here, I've got some selected weak acids, their Ka values, and their pKa values. Just if you recall, the pKa is equal to negative log of the Ka. So that's where these numbers came from. So the one would come from a table of Kas, and you can readily figure out what the pKa's are just by taking the negative log of the Ka. Okay? So deriving from the Ka expression, we get the Henderson Hasselbalch equation. pH equals pKa plus the log of the concentration of the conjugate base, A minus, divided by whatever the weak acid is. These are a bunch of different weak acids, and so that's going to go in the bottom term, and then whatever its conjugate base is will go in the top term. So here's why this equation is so powerful. Every time you have a buffer, this is the equation you should be thinking of. All right, as soon as you see the word buffer, or as soon as you see an acid and its conjugate base, you should be thinking of this equation if you need to calculate pHs. And here's why I like this equation. It's like having a machine that has two knobs on it. It has a coarse knob, which means you can roughly adjust the pH depending on the first term, and then it has what I call a fine control knob. Okay, so the coarse control knob, what it lets you do is it lets you get in the right pH range, and then the fine control knob lets you dial in exactly what the pH should be. So here's how this works. You've got this table of selected acids, and you got pKa's. So if you want to make a buffer, let's say that's 4.3, then you just look in your table of weak acids and you say, all right, find me a acid that has a pKa that's close to 4.3. Well, none of these are exactly 4.3, but benzoic acid is pretty darn close. It's 4.2. So the first decision we have to make is which acid do we use, and that's based on the pH of whatever the buffer system is you're trying to make. So if you're trying to make one that's 4.3, I might pick benzoic acid. I could pick acetic acid. In fact, the range you have is plus or minus 1 pH unit from the pKa. And if you recall, that's called the buffer capacity, or the buffer range. Okay, so the buffer range is how far away you are from the pKa. So you can make a buffer that's effective in, let's say, the nitrous acid case from 2.35 up to 4.35. All right, so using the value from the table, that gives you a plus or minus 1 pH unit away from that, which you can make a buffer from. All right, so if we want to make a buffer that's to 4.3, we can pick either one of these as our buffer system. And then depending on what we're trying to do with it, if we're trying to keep it, if we're adding acid to it, that will impact which of these we might take, or if we're adding base to it, that'll impact which one we're going to take. But the point is, I've got two possibilities I can choose from. And usually you want to pick one kind of in the middle of the pH range, so benzoic acid's probably going to be a good one to choose if we want one that's 4.3. If we want one that's 4.6, I'm going to pick acetic acid. Okay, that's the coarse control. That's the pKa value. That puts you in the right range within 1 pH unit of where your buffer is. Then the fine control is this second term. Okay, and the reason why this is the fine control is you can dial in the ratio of conjugate base and conjugate acid to say what the pH actually is. Now, if you haven't figured this out already, where does this plus or minus 1 pH unit come from? Well, the plus or minus 1 pH unit comes from if the log, the second term is log A minus over HA. If this ratio, HA over A minus, is 10, in other words, the A minus is 10 and the HA is 1, then the log of 10 is equal to 1.0, plus 1.0. And if this term, log A minus over HA, if that parameter right here is equal to 0.1, so in other words, we have 1 divided by 10, log of 1 divided by 10, that's equal to minus 1.0. So what this is really saying is this ratio can vary between 0.1 and 10. So we have actually 2 orders of magnitude of concentration from 0.1 up to 10. And as long as we're within that ratio range, we can maintain the pH plus or minus 1 pKa. So our coarse control is we pick a value that's close to our pH that we're trying to make our buffer solution, and then our fine control is we dial in this ratio based on the molarities, or, as I'll show you in a second, we can use the number of moles. Okay, we can also use number of moles instead of molarity. So think about this formula here, log of, I'm going to use big brackets here, number of moles of H of A minus divided by volume of solution, of buffer, divided by number of moles of HA divided by the volume of solution. Remember, a buffer solution is one system, right? So because it's one system, the volume of the solution cancels each other, and I can rewrite this as log number of moles of A minus divided by number of moles of HA. So I can either use molarity, moles per liter, or I can use number of moles. Either one of those is fine in a buffer system because it's the same solution. Okay, so the bottom line is, from a ratio of 0.1 all the way up to 10, in terms of the number of moles of A minus ratio compared to the number of moles of HA, and remember, this is moles, or it could also be molarity. Molarity of A minus ratio molarity of HA. So anywhere within that 0.1 to 10 range, a factor of 100 range, we have fine control, so we can control carefully what the pH is once we've picked a certain pKa. Okay? So basically this powerful equation, what it lets us do is it lets us dial in close to the correct pH by using an acid that has a pKa near the value we want. And as you can see, it can be acidic, but it can range all the way up into the basic. I can have ammonium ions, which has a pH of 9.25. So we can have acidic or basic things by choosing this coarse value and then dialing in the exact value using the fine control. All right, so we're going to take a look at an example problem and show you how to do that. So let's see, we're asked in a lab to create a buffer system with a pH equal to 6.25. Describe how you would make that buffer, include any needed calculations, and state specifically which reagents we would use. So if you want to stop this video and take a look at it and see if you can think your way through this, why don't you can actually start doing some calculations, and I will come back and actually do this problem. All right, we're back. We're trying to make a buffer system with a pH of 6.25. So I'm going to look on my table and I say, carbonic acid is within 1 pH unit. In fact, it's not that far away at all. So that's the obvious one to choose. So my buffer is going to be made up of carbonic acid and its conjugate base. So let's figure out what that is before we plow any further along with this. So carbonic acid is H2CO3 aqueous plus H2O liquid is in equilibrium with, remember, it's an acid. That means it's giving up a proton. So it's going to be HCO3 minus 1 aqueous plus H3O plus. Okay, so carbonic acid, a buffer system is going to consist of the carbonic acid plus the hydrogen carbonate ion, HCO3 minus and H2CO3. That's going to be your buffer system. So your A minus is going to be HCO3 minus and your HA is H2CO3. Okay, so we've established which acid we want. That's the first number. That's the coarse adjust. So that's going to put us around a 6.4 as my pH, but I want a 6.25. So what that means is I need to figure out what's the fine adjustment that I need to make with the actual ratio of these two things compared to one another. So let's go and rearrange the Henderson Hasselbalch equation. So pH minus pKa is equal to the log of A minus divided by HA. And now I'm going to fill in the numbers that I have. So I want to have a 6.25. So 6.25 minus 6.35, which is coming from the table. That's the pKa of the acid. And that is going to be equal to log A minus divided by HA. This is equal to minus 0.11 equals log A minus over HA, and maybe I should be some more specific here. So that's actually equal to log of HCO3 minus divided by H2CO3. Remember, this is the equation, just sort of a general weak acid and its conjugate base. This is the specific one we're dealing with. All right, so how do we get rid of this negative 0.11? How do we get rid of this log term? If we take the anti-log, that's 10 raised to whatever power there is. So I'm going to say 10 to the minus 0.11 is equal to the concentration of HCO3 minus divided by H2CO3. And if we take that value, that is equal to 0.776. All right, so what does this number mean? That is the ratio that you need between these two things in order to give you a pH of 6.25. Now, first thing you should notice is the 6.25 is a lower pH than the pKa. So in other words, it's more acidic. So that should make sense. It should make sense I need more acid than base in order to give me that lower pH. So that number is less than 1. If it was 1, you'd have the exact same amount of acid and base. But because it's less than 1, it tells us we've actually got a little bit less of the conjugate base, and we have more of the acid. That's why it's a little bit less than 1. Okay? So that's the first thing we should notice. And the next thing we need to figure out is which reagents do we want to use in order to make this? Okay, so the number of moles of HCO3 minus compared to the number of moles of H2CO3 has to equal to 0.776. All right, so we can go and use some starting amount of acid. Remember, this is moles or molarity. So if we know that we have 1 mole of H2CO3, we can use 0.776 moles of H2CO3. We can use anything that will give us this ratio. It doesn't have to be starting with 1 mole. And you might ask, well, where would the HCO3 minus, where would that come from? Well, a typical way we would do this is we would use a salt, so something like NaHCO3. And why do we pick Na or lithium or potassium? Because that's a neutral salt. It's not acidic or basic, so it's not going to change the pH. That's a spectator ion. It's going to dissolve in solution. And when we create a solution with this, it's going to be Na plus HCO3 minus. So we'll have our conjugate base. They're in a 1-to-1 ratio, so whatever the number of moles of this is, I'm going to end up with that many moles of the HCO3 minus. All right, so that is the power of the Henderson Hasselbalch equation. We have a coarse control knob, which we can use to basically dial in close to the correct pH, and then we have this fine control knob of the ratio of acid and base, which we can use to give us the exact pH buffer system that we want to make.